Okay, so as I was saying, and I'm sorry I have to say it again for the recording, the only idea in this chapter is Newton's third law. The only new idea is Newton's third law. And the basic idea of Newton's third law is that a force is not simply something that is exerted by an agent on a system, but also and inevitably something that the agent is exerted on by the system. Okay? That is, there is no such thing as A exerting a force on B without B exerting a force on A. Every single force involves two things at the same time: the agent and the exerted on, and the exerted on and the agent. In other words, I can't touch you without your touching me. It's impossible. If I'm touching you, then you're touching me. If I'm pushing on this table, the table is pushing on me. It's not revenge, it's not response, it's part and parcel of the same thing. Okay, so he has a number of mechanisms, a number of devices whereby to try to get this into our heads when we're studying this for the first time. One of them is to put a little box, all right, around things that are the system and things that are outside the system. And you can see his technique here. His system consists, in this particular case, of A and B with an external influence from C. And you can see that C is impinging on both A and B, but A and B are also interacting. And when A interacts with B, B interacts with A, and that's what he means by drawing those two lines between A and B. Okay, so as a physical example that we're going to be doing some probs on, we can think about ropes and pulleys. So the rope is pulling on the that block A, okay, and you can see that it's pulling on block A because A is accelerating this way, and that's the only force in the sideways direction. But the rope is also pulling on the pulley, and the pulley is pulling on this rope, and this rope is pulling on this block B. So all those interactions are happening all at once. In general, we're going to have to take a lot of them into consideration. Now, in this chapter here, we're going to keep some simplifying assumptions, which we're not going to relax until we get to actually discussing how pulleys work and how we make them turn and so on when we get to rotational motion. So we're going to consider that pulleys are both massless and frictionless. So it doesn't take any force to make the pulley turn. It just turns without any friction at all, and without any necessity to exert any torque on it, which we don't know about yet. We're also going to consider that all all ropes and strings are massless. So that it also doesn't take any force to exert to accelerate the rope or the string. In that very simple case, then A and B are the only objects that actually have mass, and all the pulley does is change the direction of the force that is exerted. And all the rope does is transmit the force from A to B and from B to A. Okay, so Newton's third law governs every single interaction in the universe. Okay? So every force is a member of an action-reaction pair. And it's an unfortunate phrase because reaction makes it sound like you pushed on me and then I think about it and I think, oh yes, I'm going to push back. And you don't do that, okay? The push happens at the same time, okay? So for example, suppose you take your fingers and you try to bend them backwards. I always like to use this physical example because you can do it with your very own body. I can only bend my fingers back a certain way. Some people can bend them back farther. But anybody can bend your fingers back more if you press them on a tabletop. So clearly you're pressing on the tabletop, but the fact that it bends your fingers back further shows that the tabletop is also pressing on you. So that's an example that I like to use. Okay, so this is another of his little diagrammatic mechanisms here. What he does is he has two free body diagrams here. Okay, this is the tension force of R on C. This is the tension force of C on R. You should always use this kind of label. That way, the way it's obvious to you which two forces are a third law pair. But to make it even more obvious, he connects the two arrows with a dashy line. to indicate that they're a third law pair. So for example, when I design a quiz on this chapter, which I need to do for next week, one of the things I'm going to be asking you to do is to identify third law pairs. And you'll have to say, well, this force and this force are a third law pair in order to answer the question properly. Okay, why is it important? Well, because you can't get the right answer. Okay, so reading questions. Oh, which reminds me, somebody was going to tell me about an incorrect thing in the online homework last time. Somebody told me of this, and I said, I will try to remember, but if you email me, I can make sure nobody emailed me, and of course now I've forgotten everything.
Oh, we talked about it in class.
Yeah. Well, it doesn't matter. Whatever, okay. But if you've lost points because of this, by all means email me and I will restore your points. I mean, electronic homework systems can be wrong. I mean, anything can be wrong. I mean, I can be wrong too. But I can always fix it, point-wise with Gradebook. Because I'm in charge of Gradebook. Okay, let's talk about these slides, right? So we're starting out here with interacting objects. It's clear that when I have a hammer and I hit a nail with it, that I'm hitting the nail.
Yep.
But it's also clear that the nail is hitting the hammer. How do I know this? Well, suppose the hammer that I use is a glass hammer. Yeah. I bet you the glass hammer is going to shatter. Because there's a force exerted on the hammer as well as on the nail. So that's how we know that at the same time, the nail exerts a backward force on the hammer. And that's why they say right here, imagine hitting the nail with a glass hammer. Ah!
But would the nail still go in though?
Depending on how much force you hit it with, absolutely. Absolutely. And exactly the same amount of force that you're hitting the nail with, that's how much is hitting the hammer with. The two forces are equal and opposite. When you hit a ball with a bat, the ball is hitting the bat exactly as much as the bat is hitting the ball. When your chair pushes up on you to prevent you from sinking into the chair and falling to the ground, you're pushing down on the chair is pushing up on you. And those two forces are equal and opposite. Okay, so here we have two objects, an A and a B, and they're in contact. And we know from all our work on free body diagrams that whenever two objects are in contact, they're exerting a force on each other. Okay? So for example, these two objects are touching at one surface. Therefore, they're exerting surface forces on each other. At the very least, they're exerting normal forces on each other, preventing the two from interpenetrating. So I can say that this is the force that B exerts on A, and this is the force that A exerts on B. And I always use this notation because it's easy and it's clear and I won't forget it. Okay. So whenever I have a pair of forces like this, I always label them FB on A and A on B. That way, I know that they're a third law pair, and I know that their magnitudes are equal. So once I put those two forces into my second law equations, I really only have one unknown, and that's a single magnitude of B on A and A on B. One of them is going to show up in the diagram of B. One of them is going to show up on the free body diagram of A. They'll be in two different free body diagrams, and therefore in two different second law equations. One of them will show up with a minus sign, but the magnitudes will be the same. So this isn't adding an additional unknown to solve for. It's actually eliminating one. Okay, so in general, if we've got a system which is a single object A, it can have a bunch of different forces on it from the environment. But we will remember from our study of how to draw free body diagrams that every single force requires an agent. So for example, when I stand here in front of you in the classroom, there are two forces on me. And what are those two forces?
Gravity.
All right, gravity is pulling down on me. That's the entire Earth pulling down on me with a force equal to my weight.
Mm-hmm.
Right? There's also
no force.
A normal force, I'm touching the ground. So therefore the ground is exerting a force on me. Okay? You can always figure out how many forces there are because you put in gravity, and then you put in one force for every touch, 2 if there's friction, and then you stop. Okay? So there are 2 forces on me. What are the 2 agents of those 2 forces? What are the things that are exerting those forces? First off, my weight force. What thing is exerting that? What's the agent? The earth. The earth. The earth is pulling on me. Okay?
Oh, okay.
Yeah. Okay? Everybody all right? All right. What's the agent for the normal force? The floor, the ground. Yeah, exactly right. Exactly right. Okay. So I would label those 2 forces as Fg, which means, the gravity force, and F or normal, okay, from the floor. And those 2 forces have 2 different agents. What would be the third law pair forces for each of those 2 forces? Well, we can figure it out because third law pair forces are always of the form Fa on B equals Fb on A. So the gravity force on me is the force of the earth pulling on me. What's the third law pair? Me pulling on the earth. What's the other force? The other force was ground pushing up on me. What's the third law pair? Me pushing down on the ground. And you could tell that force were there if, say, the ground were, I don't know, squishy. You could see that my force on it would squish it down a little bit. Now, the force of me pulling up on the earth, you can't really tell because the earth is so giganto-enormous that you can't tell that I'm exerting a force on it. Okay? Okay. All right. So here's his little diagram. Suppose you have 2 objects that you're actually interested in, A and B. Like, for example, those 2 blocks that we were talking about. If you're interested in the dynamics of both of those blocks, you would want to do a free body diagram of each block. And each block has gravity on it, has the floor on it, and has the other block pushing on it. Okay? So suppose we were to do a free body diagram of, can you see this? So here's the 2 blocks, A and B. This was the picture that we had. So now suppose we do a free body diagram of A. What are all the forces on A? Well, we've got the gravity force on A. Let's call that FGA. I'm not going to call it FG because I've also got a gravity force on B. And I don't want to call this one FG and then call this one FG because that's 2 different things. Never name something 2 different things the same thing. Always a bad technique. Let's see. There we go. All right, so we got the gravity force on A. Now, what's it touching?
Ground.
It's touching the ground, so I'm going to put in the normal force on A. Yeah. And it's touching B. So I would have a force of B on A, like that. Now, presumably, there's another force, otherwise this thing is accelerating to the left. But this is all I know from this diagram so far. I can also do a free body diagram of B. Tell me all the forces on B.
Gravity.
We've got gravity, and I'm going to call that FGB. Normal force on B, we're going to call that N sub B. And I have FB on, A on B. And what do I know from Newton's third law? I know that the magnitude of FA on B equals the magnitude of FB on A. Those 2 magnitudes are equal, and the directions are opposite. You can see the directions are opposite in the diagram. We'll do a lot more interesting examples than just this one. I promise. Okay. So here they're giving you a different set of, they're giving you a different system that you're interested in. They're saying, okay, there's a hammer and there's the nail. And I'm interested in the motions of the hammer and of the nail. But I'm also interested in all the forces that are on A and all the forces that are on B. So that I could draw a three-body diagram. So suppose C is the earth. Well, the earth is pulling down on both the hammer and on the nail. But the hammer is exerting a force on the nail, and the nail is exerting a force on the hammer. So that's what they're trying to designate with that diagram. Okay, so what he's doing here is he's putting a box. This is, everything inside the box is the stuff I'm interested in, okay? So I need to decide, do I want to do a free body diagram of A and B, or do I want to do a free body diagram of A, and a separate free body diagram of B? In either case, I need to include interactions from external forces. And if I'm not interested in the dynamics of the Earth, then I don't need to include the forces that A exerts on Earth or the force that B exerts on the Earth. So even though every force comes with a third law pair force, sometimes you don't include those. Okay? You only include forces on the Earth if you're doing a free body diagram of the Earth. Okay, so here's his basic technique. We represent each object with a circle, with a name, a label, whatever. We identify interactions. We draw one connecting line to represent each interaction. I skip all that. I mean, do this if it helps. It's just fine. But I skip all that and I just go straight to the free body diagram. And as long as I do my free body diagram the correct way every single time, I will always get the right answer. I want to draw your attention and the attention to those of you who are listening to the video, if there is anybody listening to the video, to the fact that I put up on the blackboard an additional document, which is how to draw a free body diagram. It goes a little bit farther than we've gotten so far because it includes advice for what to do when there's rotations. We're not doing rotations until we get to chapter 8 or 9 or whatever it is. But you can follow the advice that's not for rotations right now. Okay. All right, so here we have a person pushing a crate across a rough surface. All right, let's think about what we want to put in. It's kind of like the example we just did, because we've got two objects on the ground, and one of them is pushing the other, and therefore the other is pushing the one. So let's draw free body diagrams of both the person and the crate. Right? So here's the person, here's the crate. P and C. I like to label things. Okay, tell me all the forces on the person.
Gravity.
Gravity! I'm going to call that FG person, because I have no imagination whatsoever. All right, now what is the person touching? Touching two things. Okay, he's touching the ground. There's clearly a normal force, N sub person, preventing him from sinking into the floor. Okay? But there's also a frictional force from the ground here. How do I know there must be a frictional force? Well, we're told that it's a rough surface, but also look, he's pushing off the surface. That's actually how you walk. Okay? How do you know how you walk? Well, you walk by Newton's third law. You push the ground backwards with your feet, the ground pushes you forwards. That's what walking is. Walking is Newton's third law. Swimming is another good example of Newton's third law. How does that work? You push the water backwards, the water pushes you forwards. That's how it works. Okay, so we know that there's a normal force from the ground, but there's also a frictional force. Which direction is the frictional force? Well, notice that he's pushing the ground backwards. Therefore, the ground is pushing him forwards. So I'm going to draw a frictional force from the ground like that. Ground on person. How's that? Right? Are there any other forces on the person?
The box.
The box! The person is pushing the box forwards, so therefore the box is pushing the person backwards. F box on person. Chalk is cheap and so is ink. Use really, really explicit labels on your forces. That way you'll never forget which force is which. All right, now let's do the crate. Oh, are we done with the person? Yeah, we're done with the person. We're done with the person. We've put in one force for the touch on the box. We've put in two forces for the touch on the ground, and we've put in the only long-range force, which is gravity. And he's not touching anything else, so we're done. Now let's move along to the crate. Tell me all the forces on the crate.
Gravity.
We've got gravity. Let's call that FG crate. Because as I say, I have no imagination whatsoever. What's the crate touching?
Ground.
It's touching the ground, so we must have a normal force preventing the crate from sinking into the floor. So let's call that N sub crate. Because as I say, I have no imagination whatsoever. Is there a frictional force from the ground in the crate? Sure there is. Okay, which direction will it be?
In the same direction as...
No. Remember, the friction prevents it from accelerating this way. So this is going to be this way. So that's F sub ground crate. And finally, there is clearly a force from the person pushing the crate that way. So I'm going to put that in as F, let's see, box, why did I call it box? I should have called it crate. F person on crate. And we know from Newton's third law that F person on crate equals F crate on person. I can either write this as absolute magnitude with hats, or I can leave off the hats and just write it without hats and just as the magnitudes. And those two magnitudes must be the same by Newton's third law. So if I were to write down Newton's second law for the person and for the crate, there's really only one unknown from these two different forces. Everybody good? Mm-hmm. Great. Let's see what they say the answer is. They might actually be right. Let's see. Amazing! Look at that. We've got the push, which goes between the person and the crate. We've got normal and friction from on the person and the crate from the surface, and we've got gravity. Exactly what we said. I didn't draw this little diagram for you. I just did the free body diagram directly. Okay, here is their free body diagram. Okay, two free body diagrams, one for the person, one for the crate, and notice each one is labeled. That's good, because otherwise you forget halfway through the prob which it is you're doing. Okay, he's got actually one thing that I forgot to put. Does anybody see my error that he's actually got right here and I didn't?
His axes.
He's put axes, and I forgot my axes. So I'm going to put in my axes. I'm going to use the same axes for both. I'm going to call the x direction that way and the y direction that way because I'm sort of copying what they're doing here. Notice that he's got a force of friction on the person, F sub P, and that's exactly what I've got here. Force of friction on the crate, that's exactly what I've got here. Force of crate on person, force of person on crate, exactly what we've got here. Normal forces and gravity forces. Exactly what we've got. So we've done good. The only thing we left off was the axes. Okay, here's what I was just saying a minute ago. How do you walk? You walk because the ground is pushing you forwards. You push the ground backwards, the ground pushes you forwards. And that's static friction, not kinetic friction. Why is it static friction? Because unless your shoes are actually slipping on the ground, those two surfaces are not moving with respect to each other. Okay, here are other examples of propulsion using Newton's third law. This is how rockets work. Newton's third law. They whoosh gases out the back end. The gases whoosh the rocket forward. I promised you we would explain where thrust comes from when we got to chapter 7. Well, here it is. All right. Cars move by pushing the ground backwards with their tires. And we know that that's how it works because suppose you're on a pool of oil. Well, the wheels just go slip, 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 and you don't go anywhere. Okay, so here is Newton's law, third law in all its glory. And here's the catchy phrase, for every action there's an equal but opposite reaction. And as I say, the problem with this phraseology is it makes it sound like it's revenge or response to the force. And it's not. It's part and parcel. They're all the same thing. There's no lag in between. They happen at the exact same time. There is no force that's one and only one thing on one thing. It has to be on two things at the same time. And so we can write it up like this. They're all of the form FA on B and B on A. Okay, so if we've got a ball that's falling, I don't have a ball, but I have a chalk. We've got a ball that's falling, a chalk that's falling. What's happening? I let go of the chalk. It is pulled to the earth. What is it pulled to the earth by? It's pulled by the Earth's gravity. Mm-hmm. At the exact same time, the ball is pulling the Earth up. But the Earth is so gigantic that we don't observe the acceleration of the Earth due to the ball. Okay. Here we have a silly question. A mosquito runs head on into a truck, splat, which is true during the collision. Okay, well, let's look at A. The mosquito exerts more force on the truck than the truck exerts on the mosquito. Well, that's ridiculous. The truck exerts more force than the mosquito exerts. Well, that's also ridiculous. When the mosquito hits the truck is hitting the mosquito. They have exactly the same force on the mosquito as on the truck. However, the mosquito is so tiny that the same force on the mosquito makes it go splat, and the truck doesn't really care. So the correct answer is C. Okay, what about the acceleration as a result of this force? Well, the acceleration of the mosquito is big because it was moving in some direction and now it's only moving with the velocity of the truck, right? But the truck doesn't care, right? The mass of the truck is so enormous that the acceleration is tiny. Remember, the acceleration is equal to the net force divided by the mass. So even if it's the same force, if the mass is huge, then the acceleration due to that force essentially is nothing. And that's right here. So A is equal F over M. The F is the same, but there's a big difference in the mass of the mosquito and the mass of the truck. Okay, here we have two boxes A and B. And in this case, we can see that the joint project is moving in this direction as accelerating in this direction. Okay, so I'm pushing on A. So there's a force of hand on A. There's also a gravity force, a normal force, and it's a frictionless table, so we don't have to worry about friction. But there's also a force on A from B, because A is touching B. What are all the forces on B? Tell me all the forces on B. Somebody say gravity? Gravity! There's gravity on B. Okay. And there's normal force from the ground on B. It's a frictionless table, so that there's no friction from the table. So that's two forces.
Force on A.
There's a force on B from A. That's three forces. That's it. There's no force from the hand on B, because the hand isn't touching B. But the reason B accelerates is that A is pushing it. The hand is pushing A, and A is pushing B. All right, let's do the free body diagrams. All right, I'm going to start with the picture. Here's A, and here's B. And here's the hand. I'm going to call that H, right? And here's the ground. And we're told that the table is frictionless, so I'm just going to write mu equals 0. All right. Now let's do a free body diagram of A and a free body diagram of B. Here's A, here's B. Tell me all the forces on A.
Gravity.
Let's call that FGA.
Normal force.
Normal from the table, so I'm going to call that NA. There's the hand force, right? So I'm going to call that push, P sub hand. And finally, it's touching B. So I'm going to write that like this. FB on A. Newton's second law in the x direction, I don't really care about the y direction, but in the x direction would be the mass of A times the acceleration of A in the x direction, right? What are all the forces in the x direction on A? Well, I can read them right off here. Oh, I forgot my axes. I can read them right off here from my diagram. I've got pH in the plus x direction, so I'm going to call that pH. And I've got FB on A in the minus x direction. Minus FB on A. And that's it. That's all that's going on in the x direction. Everybody agree?
Yes.
Great. Now let's move across here to B. Tell me all the forces on B.
Gravity.
Gravity. Let's call that FGB.
Normal force.
Normal force from the ground. Let's call that NB. Okay, those are in the y direction, so all I'm really interested in is the acceleration here. That's the x direction. So are there any other forces on B? Absolutely. It's touching A, isn't it? So I'm going to draw that in and call that FA on B. Are there any other forces on B?
No.
No, that's it. So now I stop and I write down some of the forces in the x direction on B. Oh, I forgot my little a over here. Well, that'll be the mass of B times the acceleration of B in the x direction by Newton's second law. And that better equal what? Well, I can put all my forces that are in the x direction into my second law equations. There's only one force in the x direction, that's FA on B. Okay, now we can finish the problem. Okay? What are we going to do here? Well, we're going to use our second law equations to find out what the motion of these two blocks is. Okay? I know that presumably I'm given the mass of A and the mass of B, and presumably I'm given how hard I'm pushing. Okay? Suppose I want to find out the acceleration. How do I find out that? Well, I've got two equations, and I've got two unknowns. What are the two unknowns? Well, I don't know how hard A is pushing on B, but that's the same amount as B is pushing on A. I also don't know what the acceleration is, but I do know, because those blocks are touching each other, that they have to have the same acceleration. So I can rewrite those two equations as MA A equals PH minus FB on A, and I've got MBA equals FA on B. So what I'm writing down here is that AXA equals AXB. In other words, as long as those two blocks are in contact, their acceleration is going to be the same thing. They're going to share the same acceleration. But also I know FA on B equals FB on A, because they're a third law pair. So let's just call it F. All right, now it's clear that I've got two equations and two unknowns. The two unknowns are A and F. I can eliminate F from this equation by just solving F is equal MBA. So I put that in. And then I get A times MA plus MB equals PH, or A equals PH divided by MA plus MB. And that makes perfect sense, doesn't it? It says the acceleration of both blocks is going to be equal to the push force divided by the sum of the masses. In other words, my push force with my hand is accelerating both of them. So this makes perfect sense. Okay. They've got here actually 3 free body diagrams. I'd forgotten that he does that. Let's look at those. All right, so he's doing a free body diagram of A and B and also of the hand. Notice that there is no force on B in the x direction except FA on B, which is exactly what we got. There are 2 forces in the x direction on A, There's FB on A in the backwards direction, because it's a third law pair, and F hand on A. And he's also got, for some strange reason, the free body diagram with the hand. Okay, so I jumped the gun a little bit with telling you about acceleration constraints. What's an acceleration constraint? Well, it's the idea that if two things are in contact and they stay in contact, then whatever acceleration they have has to be the same. Okay? So for example, here they have a tow truck and a car. As long as the rope remains under tension, the acceleration of the car and the acceleration of the truck are the same. If the rope goes slack, that won't be true anymore. You know, you have to learn to actually put those things in. Okay. All right, here we have a more complicated system. We've got a block A and a block B, and they're tied together with a string. As long as the string remains in tension, the acceleration of A in the x direction is going to equal the acceleration of B in the downwards direction. That's only as long as the string remains taut. But you'll always be asked to assume things like that to make problems easier. Okay, so you can use this as sort of a general technique whenever you've got interacting objects. And that's what we're going to be doing in this chapter with probs. We're going to be doing probs where you need to do more than one free body diagram. Okay, so here's a check question. We've got a car being towed by a truck, and we want to know what's wrong with these free body diagrams for a truck towing a car at steady speed. Okay, little bell goes off in our head, we hear steady speed, and what do we immediately think of? Steady speed. Steady speed means the velocity is not changing. If it's going in a straight line at a constant speed, then it's going at constant velocity. If it's going at a constant velocity, then the velocity is not changing. If the velocity is not changing, the change in the velocity is zero. If the change in the velocity is zero, then the acceleration is zero because the acceleration is the change in the velocity with respect to time. So, what must be true of all the free body diagrams? Well, they better have forces that sum to zero. They have to. Okay? They have to have forces that sum to zero because the acceleration equals zero. And by Newton's second law, the acceleration is the net force. Okay? So the first thing we look for is do all the forces sum to zero for each of the free body diagrams. And we see that yes, that is okay. All right, so that's all right. What else do we want to know? Well, the other thing we want to know is what's exerting a force on what? So if I look at the car, how many forces are on the car? 4. Okay, all right. In the diagram there's 4, but is that correct? Okay, there's got to be gravity. There's got to be normal. We've got those. We've got to have a tow force from this tow rope. We've got that. We've got to have friction. Otherwise, if we didn't have friction, then the forces wouldn't sum to zero, would they? So this so far looks okay. But there is one thing wrong with this, even just this diagram. What is it? Well, remember the dashy line is supposed to show you third law pair forces. What are a third law pair forces here physically in this thing? Well, how about rope pulls on car, car pulls on rope? Well, that would mean that this dashy line should connect here. The dashy line can never exist inside a single free body diagram because a single free body diagram is only the forces on that object. And third law pairs are always A on B, B on A. A on B forces should only occur in the free body diagram of B. B on A forces should only occur in the free body diagram of A. So those are two separate free body diagrams. So you should never, ever, ever have a third law pair which is both on the same object. That's impossible. They have to be on two different objects. So all three of these dashy lines are garbage. Where should we have dashy lines? Well, we should have a dashy line between here and here. This is the rope pulling on the car. This is the car pulling on the rope. And here. This is the truck pulling on the rope. This is the rope pulling on the truck. Okay. So I'm going to go that D is certainly true. One or more action-reaction pairs is wrong, right? What about the lengths? Let's look at the lengths. If two forces are a third law pair forces, then they better be the same length. So this has to be the same length as this because of third law. This also has to be the same length as this, but not because of third law, because of second law, because this is going at steady speed. So the forces have to sum to 0. So this has to be the same as this by second law. This has to be the same as this by third law. This has to be the same as this by third law. And this has to be the same as this by second law. Now, if you look at this arrow and this arrow, they're not the same length. So that's got to be wrong, because these two are a third law pair. So they have to be the same length. And these two have to be the same length. Well, they are, but they're both too long. Okay, so I'm going to say not only is D a problem, but B is also a problem. So this person is never going to get the right answer on their problem. Oh. All right. Here is the correct way of drawing those free body diagrams. Okay, we've got a car parked at rest on a horizontal road. The upward force of the road and the car is the same size as the downward pull of gravity. How do we know that? That's the question. How do we know that the upward normal force has the same size as the downward pull of gravity? How do we know that? Because the car is not accelerating. So that's second law. Okay? Or if you like, a special example of first law. Sum of the forces is 0 because the car is not accelerating. Okay, tension. Remember, ropes only pull, not push. Tension is what we call that. Okay, the safe is being pulled upwards by the rope, and the ceiling, or whatever the heck it is being pulled downwards by the rope. And you can sort of see that in your head, right? That is, we know that the ceiling is pulling on the safe, right? The way it's doing that is by means of the rope. We know that the rope must be pulling upwards on the safe because otherwise the safe would fall. And we know the rope must be pulling downwards on the ceiling because otherwise it wouldn't be feeling any weight. So the tension force, depending on what it is that you're talking about the free body diagram of, can be pulling in two directions at once, but it's always a pull. It's a pull upwards on the safe and it's a pull downwards on the ceiling. Do you see how it's always a pull even though it's in two different directions? That's what they're trying to draw here with this diagram. These are the stretched molecular bonds. They pull both upwards and downwards. But it's always a pull as a free body diagram force on a particular system. Okay, so this is frequently a hard thing to figure out. Suppose this guy here is pulling horizontally on the rope here with a force of 100 newtons. What's the tension in the rope? If you said 100 newtons, you'd be absolutely right. He's pulling with 100 newtons like this, and the wall is pulling that way with 100 newtons. And there's a terrible temptation to want to add those 200 newtonses together and make 200 newtons. But notice that if we replace the wall with a girl, then she has to pull with 100 newtons to keep the rope from accelerating. The rope is being pulled this way with 100 newtons and this way with 100 newtons. The tension in the rope is 100 newtons. And if we do a free body diagram of the boy, well, since he's pulling this way on the rope is pulling that way on him. Everybody see that? Rope is pulling that way on him. And similarly with the girl, since she's pulling this way on the rope is pulling that way on her. With how much force? 100 newtons. So this is an expanded view trying to make this point a little bit clearer. The rope has tension of 100 newtons. It comes from the fact that the boy is pulling this way on the rope with 100 newtons. At the same time, since the rope is not accelerating, the wall must be pulling on the rope in the opposite direction. So one way of saying that is the rope is a conduit whereby the wall is pulling on the boy with 100 newtons and the boy is pulling on the wall with 100 newtons. And similarly with the grope, it's exactly the same thing. So the rope's tension is the same in both directions. Okay, massless string approximation. All right, we're going to do this a lot. Not because we actually have access to massless strings that we get in our Magic Physics store, but because usually the mass of the string in our problems is going to be much less than the masses of the blocks. So we can neglect the mass of the string. So yeah, there is a little bit of force on gravity pulling the string downwards. But if we put that in, then we'd have to worry about the fact that the string is not absolutely horizontal. And it's just easier. And it's a good approximation because the blocks are so much more massive than the strings. So we're just going to ignore the mass of the strings unless we tell you otherwise, okay? So the string is just a means whereby A exerts a force on B and B exerts a force on A. So you can put in a free body diagram of the string, or you can say, well, I don't really care about the string. All I want is a free body diagram of A and a free body diagram of B. And in that case, I just, forget about this, and I just say, this is the tension force on A that comes from the string, or I can just say, this is the tension force on A that comes from B, and the rope is just the conduit. Similarly, over here, I would say this is the tension force of string on B, or it's this tension force that A exerts on B. And saying it that way makes it clearer that TS on A and TS on B are, with the string as a go-between, a third law pair, because these two are a third law pair and these two are a third law pair. So if you ignore the string, you can just say that this and this are a third law pair, and you can label them as T B on A and T A on B, and then that makes it clear. Okay, so if we make this massless string approximation, then we can just shortenify our problem in this way. Shortenify? You know what I mean. Okay, so here we have an example. Boxes A and B are being pulled to the right on a frictionless surface. Box A has a larger mass than B. How do the two tension forces compare? Okay, so how do we do this? Well, the tension in this part of the string has to be bigger than the tension in this part of the string. Why? Because this part of string is pulling both blocks. This part of the string is only pulling A. And we saw that here with our example. It's exactly the same kind of example. The hand was pushing both A and B. And so the acceleration of both of them together was the hand push divided by the sum of those masses. Right? But over here you could see in the free body diagrams that although the hand accelerated both of them, the amount of push on this was actually less than the total amount of push here. Okay, we can actually do this in detail. Okay, so we can actually compare the two tensions. We know that the tension in string 2 has got to be less than the tension in string 1 because this piece of string is pulling both of them. And here we go. Here are the free body diagrams of A and of B that make all of this clear. This is T1, okay? And T1 is pulling both of them. But also, T1 minus TB on A is the net force in the x direction on A. What's the net force in the x direction on B? Well, it's just TA on B. So this force is less than this force because these both have to have the same acceleration. And there you have it. Okay, so here's a hand pushing again. This is exactly what we saw before. I guess I already did this problem for you. It doesn't matter who has a bigger mass, okay? The question is, what is the net force that's accelerating them, okay? And we know that the force of A on B has to be the same as the force of B on A. So some of these alternatives we can just immediately eliminate, okay? So wherever it says, let's see, A on B equals B on A, that's good. A on B equals B on A. A on B equals B on A. Oh, that's all excellent, all right? So all those three equal signs are just great, okay? What about the force of B on hand? Could that be the same as the force of hand on B? Absolutely it has to be. But it can't be equal to force of A on B and B on A, because why? Because then there's no net force, and notice it's slowing down. So that means it's accelerating. So A is impossible. We have to have a net force. B on hand and hand on B have to be equal because B on H equals H on B. Why? Third law? Third law. Whenever you have a situation of B on H and H on B, they have to be the same. Have to be the same. Right? However, hand on B does not have to equal hand on A. All right? In fact, hand on A is 0. Because why? Handy isn't touching it. Right? So this is total garbage. All right, so we've got A garbage and we've got D garbage. How do we figure out which of these two is true? Well, notice that the acceleration has to be in which direction? Which direction is the acceleration, guys?
Yeah.
Correct. Very good. The velocity is this direction, but it's slowing down. So the acceleration has to be in opposite direction of the velocity. So if the acceleration is this way, then the force of the hand has to be bigger than the force of B on A or A on B. Yay. Okay, let's talk a little bit more about pulleys. In the intro, we talked a little bit about pulleys already. Okay, we said that pulleys in our massless and frictionless approximation of pulleys would just be machines whereby the direction of the force of tension would be changed. So here we have the tension force of the string on A. Here we have the tension force of the string on B. Notice that they're not even collinear. Okay? They're not even collinear. Why? Because this pulley has changed this from an X direction force to a Y direction force. Right? That's all pulleys will do in the massless, frictionless pulley approximation. They'll just change their direction. But we still have Newton's third law. It's just that we've got one more step to go through in our heads. We don't have to actually write these down. We do have to remember that these things are going on. In other words, the string is something that exerts a conduit whereby we exert third law forces. In other words, with the massless string approximation, the string is the means whereby A exerts a force on B and B exerts a force on A. Here's the force of B on A. Here's the force of A on B. Notice that these two arrows are equal. They're not opposite in direction, though. Why not? Because of the pulley. And if we wanted to, we could actually go through and do a free body diagram of the string. Okay, but we're not going to do that because it's just too messy. So we're just going to do that in our heads, and we're going to draw a little dashing line as if. Okay, and so these two forces are a third law pair, even though they're not even actually pointing along the same axis. But they're a third law pair anyway, if we ignore the string and pulley dynamics, because we don't really care. So that means we already know that the size of those two forces is the same. Okay, so here's our simplified free body diagram, and they act as if they're an action-reaction pair, and we were just talking about that. Okay, here we have 3 50-kilogram blocks, and they're all at rest. At rest, that means their velocity is 0. But they're still at rest, and still at rest, and still at rest, so their velocity is not changing. So that means the acceleration is 0. So that means the net force must be 0 on every single block. Okay, so tell me about the tension in ropes 1 and 2. Well, if you do a free body diagram in your head of rope 1, what do you get? You get the force of gravity on this 50-kilogram thing downwards and the tension upwards. So now we know exactly how big the tension in 1 is. It's 50 kilograms times 9.8 meters per second squared, right, about 500 newtons. Okay? Great. Now let's look at this 50-kilogram mass. Tell me all the forces on this 50-kilogram mass. Gravity and The tension in T2. And how big must the tension in T2 be? About 500 newtons, right? Because this mass is at rest.
Yeah.
So the acceleration is 0. So the forces must be 0. I get the exact same tension in 2 that I got in 1. Do you want to do a free body diagram of this one in your head? Or can you see immediately that it's also going to be about 500 newtons? Yeah. So the answer is the tension in the rope 2 is exactly the same. There's a I don't know, a sort of a inner desire to want to say the tension is bigger because it's holding up 2 blocks. But it's not, okay? This rope has a tension exactly enough to keep this mass stable, but so does this one, all right? This rope is also being pulled by the ceiling by exactly the same tension. So that ceiling is providing the balancing force to keep the rope from accelerating, and this mass is providing the balancing force to keep this string from accelerating. So different provider, but exactly the same amount of force. Okay, all right, this one's also a little tricky. The 2 masses are at rest, the pulleys are frictionless, the rope is frictionless, and rope is massless. Everybody is just happy, okay? What does the scale read? Well, if the scale is in kilograms, which is a terrible scale for force, but never mind, what must it read? 5 kilograms, well done, exactly. Whatever the force is that is necessary to keep this guy stationary, it has to exactly balance the gravity force. But there are 2 5-kilogram masses. Resist. Okay. This problem is asking us for the acceleration constraint. Remember what that is? Acceleration constraint means that because 2 things are tied together, they have to have the same acceleration. Okay. So here we have unequal masses. So if I set this up and was holding it and then let it go, what would happen? Yeah, A would go down, wouldn't it? B would go up. And you can see that because A has a bigger mass. That means that the gravity force on A is bigger than the gravity force on B. And assuming a massless frictionless pulley, the tension has to be the same all the way around the rope. And so that means that the tension on A upwards is actually a different, tension on A upwards is the same number as the tension on B upwards, but the tension minus the gravity here is going to be a negative number, and the tension minus the gravity here is going to be a positive number. So this guy's going to go down, and this guy's going to go up. So what would we say the acceleration constraint is? As long as the rope remains in tension, whatever A does downwards, B has to do upwards. Does everybody see that? Yeah. So there's not actually 2 accelerations that we need to solve for here. We might do 2 free body diagrams. We could do 2 free body diagrams. Probably would. But the acceleration of A would always be negative the acceleration of B. So that's can
it be either or?
This is weird. These 2 are the same. Oh yeah, right, E. There we go. They're trying to be tricky, but we won't let them fool us. Okay, so working with ropes and pulleys. All right, for massless ropes or strings and massless frictionless pulleys, if the force pulls on one end, the tension on the rope is the same. Right? And if the 2 objects are connected by the rope, the tension is the same at both ends. But in each case, it's going to be a pull force. According to the object, it's being pulled. Okay. Top block is accelerated across a frictionless table by the following mass M. String is massless, pulley is both massless and frictionless. What's the tension in the string? Okay. So how do we figure this out? Let's just do this problem. Yeah, there we go. You can do any prob in this book if you're just systematic. So let's do this. Here's the picture. we've got a block here, we've got a pulley here, and we've got a block here. And this is the mass M, and the top block is, okay, and the table is frictionless, so I'm going to just put mu equals 0 here, and we want to know the tension and the strength. Okay, so what are we going to do? We're going to do a free body diagram of both blocks, or each block rather. Here's the free body diagram of, let's call this mass M. Tell me all the forces on M.
Gravity.
Ah, love you. Yep. FGM. Why am I calling it FG capital M? Because I don't want to mess it up with FG little m. So I'm not going to call every force of gravity FG because that would be wrong. All right. So what else?
Normal force.
Normal force because it's touching a table. Now we are told that the table is frictionless, so I'm not going to put in a friction force from the table. So it's touching the table, and we only have the one touch force from that. But it's touching one more thing. What's it touching? It's touching the rope. Yep. And remember, ropes only pull, not push. So that's going to be the tension force this way. Let me call that T sub big M. Because I have absolutely no imagination. All right, now I'm going to do this guy, little m. Tell me all the forces on little m.
Gravity.
There's gravity. Let's call that FG little m. And there's the rope. Now let's call that T sub little m. And here's my x direction, my y direction. You know what? I'm going to call this the y direction. Because little m is certainly going to accelerate in the downwards direction. I'm just making it positive. So if I wrote down my Newton's second law equations, here I would only need a y direction equation, correct? Because there's nothing going on in the x direction. So I'm going to call it Fy little m, and that's going to equal little m times the acceleration of little m in the y direction, and that's going to equal what? Well, remember I called this positive, so that'll be mg minus t. And I'm going to write down here that T sub m equals T sub big M equals T. That's my third law constraint. It says that the tension in this rope has equal to tension in that rope. And I'm also going to write that A sub big M equals A sub little m in the y direction in the x direction. And let's just call that little a. That's my acceleration constraint. Why am I allowed to say that? Because they're tied together by a rope. So those are my two things there. So that means that I could just call that little a. All right, what about my equation over here in the x direction? I don't really care about the y direction. This is going to equal this, and that's kind of boring. I would only need the y direction if what? If there were friction, because then I'd need the normal force to find out how big friction is. But since there isn't, I don't care. So sum of the forces in the x direction on big M is going to equal the mass of big M times the acceleration of big M in the x direction. But I'm just going to call that little a, because that has to be the same as this. Right? And then that equals what? What are all the forces in the x direction on big M?
Just tension.
Just T, yeah. Okay. All right. So what do we want? Right? We want to know how big T is. Well, I've got two equations. I've got MA equals T, and I've got little ma equals mg minus T. Two equations and two unknowns. A is a positive number, all right? So how do I figure out how big T is? Well, what I can do is just solve one of these for little a, and plug it into the other one, right? So let me just divide both sides of this for little m, right? And I get a equals g minus T over m. And I can plug that in here. And I got m times little a, which is g minus T over m, equal to T, right? So that's, yeah. So taking that guy over to the other side, I got mg equals T times 1 plus m over little m. Taking that over to the other side, I get T equals mg divided by 1 plus big M over little m. So I actually have an expression for the tension. And the question is, how big is it compared to mg? And the question is so simple, I didn't even need to work through the entire problem. Well, why was the question so simple? Because I had the answer for that already here. Notice that A is a positive number because the thing is actually accelerating in that direction. So this is a positive number, so that means this is a positive number. So that means mg is bigger than t because this one kind of came in with a minus sign. So I didn't really need to solve the whole problem. They were asking something actually very simple. But I like solving problems. Hey. Yay! Okay, here we got another prob. Well, two probs. Block A is accelerated across a frictionless table. String is massless, pulley is massless and frictionless. We got them in our magic physics store. Oh, sorry. Here we are. Which is true? Does block A accelerate faster in case A than case B? Same as case A and case B, or slower in case A than case B? All right. This is actually simpler than it looks. The net force in B is 10 newtons. What's the net force here?
10 newtons times gravity.
Ooh, don't do that. Got the wrong units. Tell me all the forces on this mass.
Gravity and tension.
Gravity and tension, okay. Gravity is 10 newtons.
Mm-hmm.
But tension must be less than 10 newtons, because why? Otherwise it wouldn't accelerate downwards. We just saw that. So this one will accelerate faster because it's being pulled harder.
Mm-hmm.
You're good? Yay. All right, that's it for chapter 7. That's all there is in chapter 7.
Wow.
I know, but it was fun, wasn't it, while it lasted? Ah. All right. Oh, I shouldn't have done that. That was stupid. Okay, so now we have time for some example probs. Not a lot of time, but a little time. I'll just put this up and ask if anybody has any prob that they'd especially like me to do. Be happy to do it. Oh. So who has a prob?
I'm just going through the question. I'm going to the question.
That's fine. Take your time. All right. Okay, let's look at these chapter probs. Yeah, sure, anything you like. So the first one that from the book that I've assigned you is number 3. Steel cable with the mast lifting and girder. The girder is speeding up, and they want a free body diagram. Right. What about something a little harder? How about
4?
Sure, let's do 4. All right, 4 says, oh dear, I've got to draw something. Uh-oh. Here's block A. Here's block B. Here's a rope. Here's a pulley. Here's the other side of the rope. So this is number 4. And block A is sliding down the incline. So I'm just going to put this in as a velocity, V. And all surfaces have friction. The rope is massless. Massless pulley turns on frictionless bearings. The rope and the pulley are okay. Blah blah blah. All right. So I'm going to do free body diagrams of A and B. Okay. And you're going to help me out here. So here's A. I'm labeling them so we don't get confused. Here's A, here's B. And actually, B is easier than A, so I'm going to start with B. Tell me all the forces on B. Gravity. I love it. And I'm going to call that, what shall I call that? How about FGB? Because there's also going to be a gravity force on A, and I don't want to get them confused. All right. Now, what is touching B? All right. A is touching B. Notice A is moving that way. That means B is moving that way. Okay? How can I tell? Because they're tied with this rope. So B is moving that way, and we're told that all surfaces have friction. So if B is moving that way, there must be a force of friction backwards. So I'm going to put in FK A on B. And of course, I've also got the normal force, A on B. There's one other force on B. Tell me what it is. The tension from the rope. Well done. Exactly right. And ropes only pull, not push, so I'm going to put that T on B. I'm now done with B. That's all there is on B. B is touching this surface. I've got two forces from that, and it's touching this rope. I've got a tension force from that. That's it. Now let's do A. What are all the forces on A?
Gravity.
Gravity. I love it. Let's call that FGA. It really helps to have no imagination. Then you know exactly what your symbols mean. Right, now what's touching A? Well, there's the tension force, there's the string force. So I'm going to put that in here, and I'm going to call that TA. Right?
Yeah.
And it's touching both the B surface and the slope. All right, here's the slope, N slope. And here's the friction force from the slope, Fk slope. Those are external forces. But there are also forces from B on A. And that's the reason I did B first. Because every force that A exerts on B, B exerts on A in the opposite direction. There are two forces that B exerts on A because A exerted them on B. What are those two forces? Well, the two forces from the surface that B shared with A. So here's the normal force A on B. So now there has to be a normal force B on A. Here's the friction Ka on B. Therefore, there has to be a friction Fkb on A. Wow. Yeah. That's all the forces. Let's write down all the third law pairs. Right? Third law pairs. This guy, Fka on B and Fkb on A. There's Na on B. There's NB on A. And finally, there's T on B and T on A. So there are three third law pairs, and there's one acceleration constraint. What's the acceleration constraint? Well, we didn't put in our axes, and my bad. Oh, I guess I should do it this way. I don't know. What's the acceleration constraint? As long as these guys are tied together, what has to happen? If A moves this way, B moves that way. So what I'm going to write down is that the acceleration of A has to be equal not minus the acceleration of B. So all right, now I'm done. And I'm 1 minute over. Terribly sorry. Oh, whatever. All right, I'll see you on Tuesday. Have a wonderful weekend, and Happy New Year to everyone who's celebrating.